proposal talk, which I've asked to be 30 minutes, just to kind of keep that under, reasonable amount of time. And then we'll go into the Q&A part. These slides are numbered at the bottom right corner. So if you have any questions about a specific slide, if you could just make a note of that slide number, that kind of helps speed things up at the end. And if for some reason there's a technical glitch or you can't hear or something like that, you can go ahead and interrupt. But I would prefer if we held the questions till the end just to kind of get through the talk. So any questions about any of that? Okay. So without further ado, I think we're going to go ahead and just start. Daniella, you could go ahead and start your presentation.
Okay, and just confirming video works, audio works, and you guys can see my laser pointer in just a second.
Yeah, it all looks
Yes.
good.
Okay,
Yeah,
Perfect.
perfect.
Okay, go ahead and take it away.
Okay, well, thank you everyone so much for coming to my proposal presentation today. For those of you I haven't met, if anybody is here that I haven't met, my name is Daniella Gutierrez Easley. And today I'll be presenting my work, which is this mixture of analytical geochemistry, UEP modeling, and understanding the modes of organic deposition and preservation throughout Northern South America. So I'd like to start off by saying thank you to my committee members, many of whom I have bugged with long emails and impromptu meetings for a few years now. I also want to acknowledge Andy Pepper, who is here as a guest today. I'm not sure if he's in the meeting yet, but he's somebody that has been a close advisor of mine through chapters 2 and 3 of this project. And I definitely cite him a lot in my proposal. So right off the bat, I know the title of my dissertation sounds a little strange. During my first 2 years at U of H, I worked with Dr. Visada and the UH Center for Petroleum Geochemistry. And this is where I completed my first chapter and first manuscript to evaluate the use of GC-MS-MS to analyze carbazoles. In the fall of 2021, right over here, I moved to the CBTH project to work with Dr. Mann, and my second and third chapters here are UEP modeling and then understanding the drivers of the source rock potential from Venezuela to Guyana. All 3 chapters, though, I still consider them to be very related. Chapter 1 focuses on analytical molecular geochemistry, and this work made me really familiar with concepts in OChem and PChem. Chapter 2 then is where I can apply that understanding of things like reaction kinetics to geochemical or UEP modeling. And so finally, chapter 3 ties all of this together to answer some of the bigger questions about how organic matter was deposited and preserved in the first place on a very large scale. So each chapter really does build into the next in terms of scale and in terms of applied knowledge. So first to the carbazole chapter, and I'll just point out this little cheat sheet that I've put here in the top right corner. So here we wanted to test 3 hypotheses. First, if we don't fractionate an oil, can carbazoles be analyzed by the triple quad? Second, because the triple quad, it has increased selectivity over the previous method, which was GC-MS, will it have advantages other than the ability to just run unfractionated oil? And finally, number 3, if this new carbazole method is combined with previous triple quad methods for biomarkers, will we still get good enough resolution of carbazoles to complete geochemical interpretations? So the answer to all 3 questions is yes, and now we're in the process of author revision with Organic Geochemistry Journal. So if at this point the significance of the triple quad method still isn't clear, I think that is totally normal. So this previous method, GC-MS, molecules are injected, and then the mass spectrometer here is kind of like a screen that only allows a certain mass to charge, or MZ, to pass through. So let's say we're only allowing this orange triangle to pass. We would still get all these other molecules over here, like the purple triangle that isn't the same molecule, but it got through because it was the same size. Similarly, this green triangle here is really just a piece that broke off of the green diamond. And this is why it requires fractionation to analyze samples with GCMS to remove all of this matrix interference. So using the GCMS-MS or the triple quad, it starts off the same way and we let this orange triangle through. But here there's a second quadrupole where the nitrogen breaks everything up into little pieces. There's another mass spec. This is the second mass spec right over here. And we're only going to allow here shapes to pass that are the most likely fragment of the molecule or shape that we actually want to analyze. So here we actually want to analyze the orange triangle. We know the likely fragmentation pattern, so we're only going to allow one of those fragmentation types to pass through. And that's what you're seeing in the third quadrupole. So notice all these shapes in the second quadrupole, they had different fragmentation preferences, so they didn't make it all the way through. And this is, in this triple quad, this is how we want to analyze carbazoles because it doesn't require sample fractionation into SARA components, the saturates, aromatics, resins, and asphaltenes. So with this reduced need for sample washing and an ease of analysis, these molecules can be built back into mainstream petroleum exploration because they have strong applications to source rock lithology, thermal maturity, expulsion timing, migration distance, and the prediction of other geochemical components. So for the results, and I'm going quickly through this chapter only because it's already been completed, but we did have good success testing all three hypotheses. First one, through the process of calibration and method development, we found good triple quad precision and an accuracy of values when they were compared to GCMS. Next, without fractionation, the triple quad can still quantify carbazoles in most samples when GCMS cannot. So over here on the left, the triple quad is shown in red and the older GCMS is shown in black. So even with this base carbazole molecule in section A, we get perfect quantification and no possible quantification using the previous method in this case where we're not fractionating the sample. Even with the dimethyl carbazoles down here in B, there are peaks in the older method that align with the triple quad, but the baseline is just too high with GCMS to get accurate readings. Finally, one other thing to mention, in samples with such a low carbazole concentration that even the triple quad does require cleanup, the triple quad can still quantify these carbazoles with good repeatability when they're below the limits of quantification and detection with GCMS. So this was the additional advantageous nature of the newer method. So now moving on to the UEP modeling, where this is where I can apply this background knowledge to modeling kinetics. The overarching goal of this chapter is to deconvolute some of our current understanding of source rocks through time and space across the entirety of Northern South America. And these three hypotheses over here, they were developed based on unintentional previous inaccuracies in thermal basin modeling. So first, does focus on the Cenomanian Turonian rocks lead to disregarding other intervals of high UEP during modeling? So based on the tectonics and paleogeography, there is also the potential for widespread UEP in the Aptian to Albian sections and the coniation sections. Next, the CT boundary is always cited as the interval with the highest potential in the region, but I think that these effects are discontinuous and really limited to the western side of the study area. And finally, does the La Luna Formation extend as a prolific source rock interval into Trinidad and Guyana? The very quick answer is no, but how is that really affecting UEP modeling and what we're seeing? So this chapter is about 80% complete, and I'm finalizing the remaining UEP models and plotting the ACMEs onto lithochronostratigraphic columns right now. And then to finish this chapter, I'll generate spatial UEP maps based on individual well UEP models. So this chapter focuses on all these basins across the study area, but I will show some preliminary results later that zoom in on the UEP modeling relationship between Trinidad and Guyana. So first, this map shows the locations of well data that I have already collected from published literature, and these wells that have been determined to be relevant to the study, so they have all the necessary components. Later, I'm going to show a map that has some of my pending well data. So in the Trinidad Guyana example that I show, I am going to be using these 4 wells here from the southern basin of Trinidad from Riccio et al. In 1994. I'll use 5 wells on the Demerara Rise, and then 1 well is, for now, ambiguously located, labeled J, in nearshore Guyana. So to visualize the formation of these different basins, first I want to start in Venezuela over here with the Maracaibo Basin. The Maracaibo Basin was initially created through the uplift of the Sierra Perija and Merida Andes in the Jurassic. And then on the eastern side, Central Atlantic rifting phase affected the Guyana Basin around 150 million years ago. And this region, then again from 125 to 112 million years ago, experienced this time transpression from the equatorial Atlantic rifting phase. So after this, all these regions are in a passive margin phase until the Caribbean plate moves in. And you can see this by the black lines labeled with the white circles. So it reactivated Western Venezuela as a foreland basin around 66 million years ago, and then it did the same thing. The effects are moving in an eastern direction. Did the same thing to Trinidad around 14 million years ago, called the Middle Miocene orogeny. So the only region that still remains as a passive margin is the Guyana-Suriname basin. So during the interval I'm interested in, like I said, all regions start off in a passive margin phase. There were the central and equatorial Atlantic rifting phases, and as the Caribbean plate encroaches on the region, you can see right over here, this is where we see the deposition of the first source rocks I'll use in UEP modeling. There's the Aptian source rock deposition, and then late Cretaceous in this Trinidad and Guyana subsidence curves. So even though I'm only showing Trinidad and Guyana, the first margin to reactivate due to the Caribbean plate movement is actually Venezuela right over here at 67 million years ago. The Trinidad region is close behind with the reactivation in the Middle Miocene occurring around 14 million years ago. And finally, Guyana, potentially unaffected by Caribbean plate movement, but it's kind of a topic of debate. This still remains in a passive margin state today. So how we plan to evaluate these hypotheses, it really comes down to 2 key steps. First, we need to rebuild our stratigraphic understanding of the area, beginning in the Aptian and ending in the Maastrichtian. And this is what's going to really allow us to see what's going on with source rock continuity and to be able to split apart these source rocks on a million-year or an ACME scale. So I've completed this step by the combination of 8 individual stratigraphy columns from the literature, and then I've begun to cross-check this with recent well data. So after the UEP modeling is complete, that's the next step. I'm going to come back to this figure to plot the locations of significant ACMEs. And this will start to shed light on whether each area of potential might be regionally driven, basin scale, or globally correlative. So as I move through this project, I'll be able to keep refining this current hybrid litho-chronostratigraphic column into a more classic chronostratigraphic column. But this is definitely what I would call a working figure here. It's constantly changing. So down here, this is just an example of how the ACME knowledge is applied to the UEP modeling step. The previous outlook to ultimate expellable potential, or UEP modeling, would be the application of this 3.45 weight percent TOC to the entire 50-meter section of source rock. What we're trying to do here is first identify the boundary of ACME intervals using secondary age data. Then the organic geochemistry, like the TOC, among other things, and acme thickness can be used to model the UEP for each individual age interval. And this is one of the ways that we have worked to reduce sampling error is by the use of these acme time intervals. So when I'm looking for well data that I can use in UEP modeling, it has to have TOC, HI, and a thickness of geologic ages at minimum, and some type of secondary age indicator. Next, we go through the lengthy process of back calculating TOC and HI, and then designating certain samples by organophases, again, based on geochemistry. The final step here is to generate ultimate expellable oil and gas UEO and UEG maps, and then the ultimate expellable potential, the UEP map that represents the addition of the UEO and UEG components. So with this map down here, we do have the minimum amount of well data needed to complete the scope of UEP mapping across the region right now. However, additional data would really improve resolution in areas like Guyana. So currently, and what you'll see on the next slide is right now we have to make the false assumption that geochemical parameters are constant throughout each geologic age. So we have to rely on this older method, specifically in Trinidad. This does allow, though, for a qualitative comparison to Guyana, but it's just not useful for acme scale interpretation. So I am not sure if she is in the meeting yet, but I met with Dr. Trish Alvarez at Heritage Petroleum in Trinidad, and she asked me to submit a data request for these specific wells in Trinidad. And we just heard that she's going to have an update for us at the end of the week on access to these data. There are also 2 points on this map that are additional sources of data. Met with Dr. Liliana Lopez at the Universidad Central in Venezuela. And there's a possible lead on outcrop data right here from the Serrania del Interior. This would be looking at the Caracol Formation. Finally, one other point on this map, Andy Pepper has collected samples of the Naparima Hills source rock outcrop in Trinidad from San Fernando Park, which could also be utilized. So for the preliminary results, we start to see patterns that do exist between the two regions. And this is a smaller project I did just comparing Trinidad to Guyana. So we can't yet make any comparisons in the Maastrichtian or in the Campanian sections, but just due to this presence of UEP in the Maastrichtian, that's already significant as no previous authors have recorded source rock potential in this age interval. Interval where we can get a good comparison is the Santonian, where it wouldn't generally be described as high potential in either region, except for at one well location on each side, the Morocco one here, and then IODP 1261. Coniation is the most significant geologic age here because it shows consistently high UEP at almost all of the wells. There are always exceptions. One well in Trinidad is showing low UEP, and there's another well in Guyana for which we just didn't have any data to model. Moving down just a little bit to the Turonian, it's a little lower in UEP than the Coniation, but it's still significant that it's consistent across the study area. Moving down into the Cenomanian, it, like I said, commonly cited as the most significant interval with the highest potential all across northern South America. But looking closer here, we see pretty terrible UEP values over on the Guyana side, or sorry, on the Trinidad side, and then only one well in Guyana, IODP 1261, that's showing any significant potential. So the Albion, it wasn't a huge focus in the study, but in wells where it was penetrated, it's important to note that it has a consistently gas-prone nature to the source rocks and a gap in UEP that occurs in the middle Albion. So the deliverables of Chapter 2, they're closely related to each of the initial hypotheses. So first, the hybrid litho-chronostratigraphic column, it's going to help to identify new intervals of high UEP. Next, the UEP models created at individual wells, like the Trinidad-Guyana example, they'll show trends across the region, which are particularly important for the CT. Finally, down here, the UEP maps, like the ones seen down here in the Bakken, created by Pepper and Roller in 2021, these will be generated for each interval of interest. So some of the individual acmes, as well as for the cumulative potential from the Albion to the Maastrichtian. And finally, I just wanted to show the process I made particularly on this chapter. I've presented this work 9 times since joining CVTH. I won 2 awards in the fall of 2021, and I'm currently waiting on acceptance down here of an extended abstract for image, which would technically be published as well. So now finally down to chapter 3, this is the one that's focused on understanding large-scale drivers of organic deposition and preservation based on UEP trends. So these hypotheses over here in this chapter are very important to keep track of through all of the steps in this project because they really build into one another. So the first hypothesis is that OAE2, or the Bonarelli event, it's not uniformly expressed in Venezuela, Trinidad, or Guyana. And what I mean by that is just because there is source rock potential at the CT boundary, it doesn't mean that OAE2 is responsible for that potential all the way across northern South America and even in a consistent way within each basin. So next, I believe that the use of organophages in paleogeographic by using organophages in paleogeographic mapping, we can update some of the current less evidence-based maps. And this is particularly important for the Guyana Basin, which I'll show you in a couple of slides. So finally, an extrapolation of the West African conjugate margin UEP towards Guyana can help to evaluate the UEP of the deeper Guyana sections. This is really important, again, as recent pushes to understand the continuity of units between the condensed section of the Demerara Rise and the Basin Center, Depot Center are currently underway. So that's the first extrapolation, but there are plenty of additional potentials here. So looking at the OAE1A in Venezuela to evaluate the deep Guyana Basin, seeing CT similarities between Guyana and the Gulf of Mexico, and using that to say something about the CT of Trinidad. So movement of and extrapolation of data across areas is the goal of the third hypothesis. So what triggers an OAE? First off, is usually some type of extreme magmatic eruption. This released CO2 warms the atmosphere and shallows the water stratification, causing an increase in the anoxic section. This eruption, it also releases metal micronutrients, increasing productivity and then increasing preservation due to anoxia. So as you see, these OAEs, they definitely can contribute to increased productivity and preservation, but the part that we want to address here in this project is whether they're the driver of all CT source rocks in the area, like the La Luna, the Caracol, the Naparima Hill, and the Conje formations. So to take another closer look at what's happening during an OAE, this increased anoxic section, which favors C13 over C12, causes an isotopic excursion or a shift in the delt C13. So this is an increase in the delt C13 you see with the onset of OAE. And this is a really typical marker of an OAE. We do know that OAEs, they likely cause this isotopic excursion, but that doesn't necessarily mean they are also causing productivity and preservation. So I'm citing down here from Manuel Paez-Reyes, who's a recent UH PhD grad. He was modeling the shifts of productivity and preservation before, during, and post OAE based on cadmium, molybdenum, cobalt, and manganese. So what he observed was that despite this isotopic excursion, these shifts in productivity and preservation were found to be attributed only to seasonal changes in the water column. On a similar note, using UEP, if an OAE was responsible for source rock potential, there would be an expected peak right here at the OAE2 marker. Here, though, we see the opposite relationship, a chunk of organic lean source rock. One other perspective is a model of the upwelling effects of these large igneous provinces, or LIPs, thought to be a catalyst for OAE2. The modeled upwelling shows that on the northeastern side of South America, there's not really strong evidence that the OAE2 upwelling effects ever even reached Trinidad or Guyana. So it is reasonable that OAE2 isn't the driver of source rock potential across the region, but tectonic understanding is also very important to evaluate potential lagged effects of OAEs. For example, imagine a restricted basin that might have opened up right after an OAE and experienced an effect of increased productivity and preservation. So this potential wouldn't occur exactly when the OAE did, but the OAE would still technically be the driver, which is why in evaluating effects of OAEs, we have to look at the entire picture. So finally, for hypothesis 1, there are a few other methods which could help to evaluate the reach of OAE2. Finalizing the UEP models from Chapter 2 and using even more chronostratigraphic columns to refine my column in areas of sparse data, like the Orinoco heavy oil belt here, this would help to visualize the extent of significant acmes. Over here on the right, an integration of system tracks onto the same column would also aid in the evaluation of organic drivers. So this method's not completely set in stone, as my own TGS access to seismic is still pending. However, DSDP and ODP scientific reports contain core data where the sequence stratigraphic analysis is still possible. So in this area, eustatic sea levels rise during the Cretaceous due to the creation of the seafloor, but this increase is consistent, and I believe this is what defines a second order sequence. There are also, though, tectonic effects or tectonosequences which influence what we're seeing in terms of unconformities. So those two need to be separated from one another. So to jump into hypothesis 2, the modeled geographic transition in organofacies occurrence can increase the resolution of paleogeographic maps. So over to Kaysen down here modeling Guyana and West Africa at 101 million years ago. It's so important that we understand the shelf edge because upwelling wouldn't have occurred up on the shelf. So mapping these boundaries through time is not secondary to exploration efforts. So using organofacies transitions from the literature and from the data created during Chapter 2, I can use that information to refine previous paleogeographic maps towards a more evidence or data-driven approach to mapping. So very closely related is hypothesis 3, or an extrapolation of the West African conjugate margin UEP interpretations towards Guyana. With the deepest sections in Guyana, they've been difficult to evaluate. Either wells don't drill that deep, or when they do, the data stays very well protected. But based on a relatively small degree of rifting towards the end of the equatorial Atlantic rifting phase at 101 million years ago, West Africa was still geographically and equatorially very similarly placed to Guyana. So looking first at the amount of ODP data in West Africa, combined with the DSDP data, there are plenty of wells that could be used to model UEP. And here's just a visual example of some of the available well data from DSDP and ODP. First one is DSDP leg 14, site 144 in Guyana. And this is an example of a subsidence curve and seismic interpretation where I've marked the OAE by a red dashed line. Next, there's DSDP leg 41, site 367. This is from the Cape Verde Basin, and it has really fantastic biostratigraphic analysis going through the entire well, including the sections that we're trying to evaluate. So finally, for the deliverables on this chapter, again, closely related to each individual hypothesis. To address hypothesis 1, I'd like to finalize, update, complete the chronostratigraphic column with marked system tracks on here and a notation as to whether acme occurrences are regionally specific or basin specific, or potentially globally correlative. Also for this hypothesis are maps for each major OAE. I'm going to really focus on OAE2 and potentially build in OAE1A at 122 million years ago, but these maps would show areas that show a strong correlation to OAE, the areas that have the potential to correlate, and those areas which show no relationship to this OAE-driven productivity. To address hypothesis 2, that one is pretty straightforward. That's the updating of paleogeographic maps based on organofacies. And for hypothesis 3, we're definitely going to connect West Africa to what we're seeing in Guyana, but I'd like to create a global map with locations of identified ACME intervals, kind of similar to this preliminary example that you can see over here. So this one too, it shows some of the preliminary and anticipated results, which are that there's a tie between ACME 95 in Guyana and the Gulf of Mexico. And these both signify strong geologic controls on organic deposition and preservation, mainly because they both show a negative correlation in UEP modeling to OAE2. Next one is that West African conjugate margin can be used as an analog to the Guyana Basin at ACME 101. On a really similar note too, OAE1A effects in Venezuela over here, looking at the Mechiques member of the Apon Formation, can be used to describe and to try to figure out how OAE1A might have affected Guyana. And that would be a deeper section of source rock than is mentioned in previous literature. So finally, for my graduation timeline, what I'm doing before my internship starts is proposal revisions and submitting my first manuscript back to organic geochemistry. I am going to also be in any spare time that I have working on the UEP modeling. So internship over here, I come back, work a little bit more on UEP modeling, and I think I will be able to start writing up this second chapter in September. I have built in a lot of time for the review process with co-authors and the revision process. So I'd like to submit that one, manuscript 2, in December. Also, while the co-authors are reading through manuscript 2, I can formally start the work for chapter 3. And I've given myself 3 months to do that, where on the last month, I start writing up the third manuscript. Another buffer that I built in here is 3 months on the dissertation writing, going into submitting the dissertation and the defense April of next year, and defense revisions and graduation in May. I feel really very confident about the schedule because it has doable chunks of time for each of the tasks that I need to complete. Feel confident because I think I've built every major task into this timeline, and there are some uncertainties always in a timeline. I feel great about the acceptance of my first manuscript, but you never know. And this timeline has the buffer built into it for things like that. Same thing with the second manuscript. If for some reason there was an immediate kickback, there's a buffer for that. Moving my graduation to fall instead of December, it also allows for the gathering of more data. So I think that the potential well data in Trinidad from Dr. Alvarez should be here really any minute, but there are a couple of people that I have on list that I would also like to reach out to about data access as well. So finally, in addition to my committee, I'd just like to say a really big thank you to all the geochemists, source rock experts, and Northern South America geologists that have helped me develop these projects through really countless Zoom meetings. So thank you, everyone, and I'll take any questions you have for me.
Okay, good. Thank you, Daniella. So with that, we'll start the Q&A part of this, and I'll start out with a question about slide 16. And by the way, Daniella, do you mind recording this Q&A just so you have a record of it for yourself?
Oh my gosh, is it not recording right now?
I
It
don't,
is.
It is already. It is already.
Oh.
Yeah.
it's all right. Okay, good. Thank you. Okay, so slide 16. There it is. Okay, so you made this statement that there's sort of a negative correlation here between your UEP model and the OAE2 at a 93.6 million year. But isn't it true that, you know, these OAEs are attributed to large volcanic provinces which are erupting large amounts of metals and other things into not only ocean but also the atmosphere? So that would not be reasonable, would it, to assume that all of those effects are going to be instantaneous? In other words, there would be a time lag for all of that material to be transported over large areas, would it not?
So that is true. The OAEs, they aren't just an absolute instantaneous effect. Based on age dating projects that I've read recently, more in the fields of biology, to be honest, but they're really narrowing down the extent of OAEs to plus or minus 0.5 million years, meaning that if the OAE occurred at 93.6 million years, the longest it could last, you know, after that point would be 93.1 million years ago. And this is also backed up by the plot over here I showed where the peak effects of OAE in terms of the isotopic excursion are only going from 93.5 to 94. So even less than that 0.5 buffer on each side.
So it is relatively instantaneous on the scales of these maps then, right?
Relatively instantaneous, yeah, on a geologic scale. Yeah.
Okay. And you mentioned, if we could go to slide 17, you mentioned the Orinoco heavy oil belt, but I was a little bit confused. That's not a Cretaceous event, right? That's something that happens in the late Cenozoic. So why would that be of interest for your study? I mean, basically the heavy oil is oil that's been expelled out of the Foreland Basin. It's accumulated in very young rocks, Miocene fluvial conglomerates and sands, very shallow. So why would that have any bearing on what you're talking about with these Cretaceous events?
So one of the reasons I think it would be important is because within the study area, it's one of the things that is connecting the Barina-Superior basins, connecting throughout the eastern Venezuela to Trinidad. So we get this continual visualization of source rock continuity. So its location within the study area is important. However, there are identified source rocks in the Cretaceous section of the Orinoco heavy oil belt. You can see one down here. I think this is the Infante, La Cruz, and Guavanita. I'm sorry, the ones are really small, but so it has relevance for that reason as well.
Stop you there. What you're pointing to is the passive margin, right? That's the margin you talked about that's facing the Caribbean. But the heavy oil belt is an event that affected, you know, it's oil that expels from the Foreland Basin in the very late Cenozoic, right? So it's not where you're pointing. It's happening like millions of years later. So I think there's a confusion there about what that is. So, but anyway, I'll send you some papers on that. You can read about it. Okay, and one final question, slide 18.
I was just going to say, yeah, it would be useful to get the clarification because I think maybe like the source rocks up top here, the Oligocene and Miocene are the ones you're saying contributing to the Orinoco heavy oil belt. I was just putting the Cretaceous ones down here.
I guess the source rocks could be the same, but I'm just saying that the event that produces the heavy oil belt is something that happens very late in the Cenozoic. And you were talking about like it's some sort of Cretaceous event. Maybe you were confusing that with it probably is related to the same Cretaceous source rock. Anyway, but let's go to slide 18. Okay, so you mentioned here that you can recognize these organofacies types, but tell us, how do you do that? I mean, say you have these wells shown by the black dots. I mean, is that obvious from the geochemistry, or are all these wells have the information that you need to give it an organic organofacies type?
So I'm gonna split to one of the backup slides. To answer your question, it is generally straightforward to designate individual sections by their organofacies. That's because it's based on inorganic geochemistry. So things like aluminum, there's the thorium uranium ratio and the iron sulfur ratio as well. So there are pretty quantitative divisions between the organofacies, and they also tell us a lot uniquely about the kinetic parameters of the organofacies, because they were developed in that sense. They were developed by the Arrhenius equation. So looking up here, and I like this table because it kind of gives an overview of what the organofacies are and how they might relate to the more classic kerogen type classification. So initially choosing the organophagy is straightforward, and it is quantitative based on boundaries between what we're seeing in the trends of aluminum, for example. And then what that tells us is principal biomass descriptor, and using the sulfur incorporation, we can start to think about, and environmental age association, we can start to think about how all of those four things might indicate certain depositional environments and adjust the shelf edge, adjust the shoreline through time based on the shifts in organophages that we're seeing here.
But so you're saying that those dots you have on the map, that information is available, or is possible to extract from all those wells that you've compiled? That was my question, I guess, is it's available, or it's there for you to interpret?
Definitely. I'll say there are a very limited number of wells that don't include any kind of inorganic chemistry that could be used to designate organophages, but the vast majority of these wells, they do have that data.
Okay,
and
good.
Would be we wouldn't even be able to use the wells for UEP modeling if they didn't have the indications towards organophages, because it's part of the UEP calculation.
Okay, with that, I'll pass to the next person if someone would like to just jump on.
Let me ask a couple of quite general questions then before you delve into more specific topics. So, Daniella, very nice presentation, first of all. I really enjoyed it. I have a couple of questions related to your UEP method, like your method for computing, for calculating UEP. I'm very much not familiar with it. And so for me, it's even unclear how much of it is based on, like physics, chemistry, thermodynamics, and how much of it is instead just a like empirical correlation of those governing parameters that is derived from empirical observations.
Sure. I also have a backup slide for that. Let me pull this up. I don't know how to change the permanent display settings.
It's fine. Don't worry.
Okay, so to generally answer your question, it is based on laws of chemistry, and everything throughout the development of the process of these UEP calculations has been to reduce risk by interpolation over extrapolation. So it started off the understanding of the relationship between temperature and time started off with these assumptions that are based in chemistry, and they weren't showing to be valid in the literal geologic setting. And so through time and through these models, through the development of new models, we finally get to So and Easley. I know I said it wrong. 1975, this is where they came up with the Arrhenius kinetic modeling, or the use of the Arrhenius law in kinetic modeling. And this is the standard today that is used to understand the concentration of kerogen at any given time. So definitely based in fundamental chemistry law, the Arrhenius law. On top of that, though, to build the UEP calculations, the way that these were created was this understanding, and I think it is this little, just have a bunch of screenshots from the literature here, but when this was developed, they're saying they're favoring this third type of calibration that is based on laboratory and field data, just because the generation of hydrocarbons is so unique and it's specific to an individual source rock, and they didn't want to go with any kind of vagueness in the creation of their algorithms. So the algorithms here are built on field and laboratory analysis, the field data being from, I think it's something like 25 different basins all over the world with 60 temperature points, temperature time correlation points at each of those, within each of those basins. So a lot of field data.
So just to ask a follow-up question for an extra layer of clarification. So do you end up with like a generalized, let's say, equation, and you input the parameters of your source rock of interest, of all your source rocks of interest, and you get out the UEP? Or do you need to recalibrate the equation for each specific well, for example?
There is, so as we're going through the calculation, there is kind of a calibration that takes point midway through the UEP calculations, and that's the transition of the Tmax value into the standard thermal stress. So the relationship between those two things, Tmax, let me think how to, so the relationship between Tmax and STS, it is theoretical. And this is the part in my proposal that I think I described as proprietary or yet to be published from This is Petroleum System, is just this relationship between Tmax and STS, again, has been refined through the collection of just a ton of well data from Andy. It's just he hasn't published that yet. I you know, respectful to my advisors, so I'm not going to publish that. But that would be the part in the calculation where you stop and you calibrate to this geographic specific thermal heating regime.
Okay, perfect. Moving on from this, if you can go to one of your slides where you have an overview map with the location of the wells you're using. I think it's 7, something like that. So my understanding is that, like, once you have computed the UEP for all these wells, you will try to correlate, so to see how much they correlate across the various wells, across the various basins. And I think that's a very, very, very interesting part of your project. However, I think that you have like quite a few wells for Trinidad, for the Guyana and Suriname basins, but for the other basins, you tend to have quite few and sparse wells, and so there is a chance, there is a risk that you will have some like a selection bias to those wells. That well has been drilled there because the subsurface conditions there are peculiar. And so how much can you be sure that the result of your analysis on that individual well is representative for the whole basin?
Sure, that is a very good point. I will definitely admit that it is looking a little bit sparse through here. The wells that I wanted to show on this map were not only the wells that I have collected, but those that I have processed and have determined to include all the necessary parameters that I need for UEP modeling. So it's again kind of another one of those working figures where between Andy and I, we do have well data a lot more in the Barina Sapure, kind of in this southern area down here. We're still a little bit limited on the Guarico subbasin, but there are 2 or 3 wells there. We just haven't fully determined them to be applicable to the UEP modeling. But this is one of the sources of uncertainty in making the UEP map is uncertainty that we've captured this geographic variation. And what I will say is that based on seismic that we've seen and based on lithostratigraphic columns and even chronostratigraphic columns, there's not a strong continuity of units in the Maturin subbasin, for example, but there is a strong continuity between the Guarico subbasin and the Barinas Apure basin. So you wouldn't necessarily need as many points in those that you would in areas of large variation like Trinidad.
Perfect. Thank you very much.
Thank you.
Okay, so the next person, just feel free to jump in with your questions.
Yeah, Daniella, I want to start, I guess, by saying very nice presentation, very nice slide graphics also.
Thank you.
Got a few questions for you. First of all, when you're determining the occurrence of source rocks lithostratigraphically, it's pretty straightforward. You know, it's TOC and Rockefeller and this kind of stuff. When you're determining them chronostratigraphically, you run into some additional problems, and that involves the age, of course. And so my first question for you is, what is the, can you comment on where you stand in terms of good age resolution and how you're getting that age resolution? Is it dominantly biostratigraphic? And is it modern zonations? Is it dominantly radiometric? And do you have good radiometric data and so forth?
So I want to skip through this slide to the last bit over here about the observational or random potential error to answer this question. So this manual division of geologic ages, it does come with uncertainty, and you're absolutely right about that. And we're reducing that uncertainty by the use of additional age methods. So the ones that I have started using in preliminary work and have my eye out for are, like I showed in the West African conjugate margin map, the overlapping biostratigraphic windows in a given well to help constrain the age. Also using local rates of sediment deposition, which actually, that's on a different backup slide. Ash beds, and then there's also the potential use of Belmont AI assisted software. So this is what Andy uses in his work. I don't currently have access, but it's been an ongoing process to gain access to that. So those are some of the things right now that we're using to constrain the age. But there's always going to be some level of uncertainty, I think.
Yeah, let me go into that a little deeper. I mean, what you did is you listed the ways to determine the age of a sedimentary section. My question for you is, what data do you actually have for these sedimentary sections? What data do you actually have already for these sedimentary sections that allow you to confidently say what the age is? You know, so much of what you're going to turn out for your dissertation is going to be a function of how good your age resolution is.
Right.
So what is it you actually have in hand currently? And the AI work, Belmont AI is very useful, but its quality is a function of what you put into the system. Mm-hmm. And so my question is, what do you actually have so far, hard data, to give you that age resolution?
The two that I'm using currently at this point are the biostratigraphic windows from the same well where I'm getting the data, and then the local rates of sediment deposition. But I think, as you're implying, these are not absolute. These are more relative age indicators that I'm using to sort of pick apart the coniation section, for example, into individual acmes. So I would appreciate definitely any suggestions you have for me on that, because that is the largest source of uncertainty in this project. And I'm really looking to try to reduce that in any way I can.
Yeah, I think the key is that, I mean, particularly when you're compiling data from a large number of studies, the zonations that, I mean, the biostratigraphers that did the work, of course, are quite different from study to study. The zonations that they did are different. The age resolution that those zonations apply to, particularly in the Cretaceous, can vary all over the place. So I guess my recommendation there is to make sure you know what you have instead of assuming that you have decent ages. And the other question is a little bit related to that, and it's sort of related to the basis for Andy's work, and it's sort of a simple question: why is an acme 1 million years? Why is it not 1.5 or 2 or 5 million years? Is there a geologic rationale for picking that, or does it just seem like a nice round number to use?
So with the terminology between, and I mix them a lot, I mix them up a lot in my presentation, but the acme is just the moment of maximum deposition, separate from the time interval over which it's occurring. So what we're trying to identify is acme's, moments of maximum deposition, that happen to occur within each million-year age interval. So it would be the same as if we just used million-year age intervals over on the y-axis, but instead we wanted to keep that strong connotation towards peaks of deposition during the million-year intervals, which is why we call them acme time intervals.
Okay, so the actual maximum deposition period is an instantaneous thing that happens to occur within the 1 million year segments?
Yes.
Okay, and when you say that OAE2 in these sections, it does not have a particularly high UEP, what you're in effect saying is that there has been no clear identification of a maximum organic rich deposition cycle within that acme interval that contains the OAE2. Is that correct?
Right. So within that interval, or I include the next interval just because I know that there is a potential window for an OAE that is 0.5 million years. And since OAE2 occurs at 93.6, it could extend, you know, up into the next acme above. But yes, I agree with what you're saying. We would be basing it on a peak that occurs right after that point.
Okay. Then last question. This goes back to chapter 1. You didn't present it here this morning, but in your proposal, you talked in the paper also. You talked about the relationship that exists between some of these carbazole ratios and various characteristics of crude oils that can be generated, such as oil gravity and this kind of stuff. My question for you is sort of a vague one, I suppose, but why do those relationships exist? Why is it that it's possible to correlate carbazole ratios, for example, with migration distance in some case, or to correlate carbazole ratios with the specific gravity of an oil that a source produces?
So the first one has to do with the shielding of the carbazole molecule. So if you look at the base carbazole molecule, can you guys see my mouse? If I keep it off of laser mode, you can see it moving.
See the mouse, yeah, but it's not moving.
I see it moving.
There we go. I got it.
I'll just go ahead and switch to laser. So looking at the carbazole molecule, this is the base carbazole molecule, and then it builds up as one methyl group is added to it, 2 methyl groups may be added to it. So I want to point out this nitrogen right here. Think of not the correct organic chemical terms, but this is kind of the weak point of the molecule. It's the polar point that wants to stick to everything it passes by. This nitrogen wants to bond with any of the clay as it moves through the carrier bed. So there are certain things that can protect that nitrogen molecule or shield it. For example, if you had one methyl group coming off of the first position, this would work to shield that nitrogen. It would work to partially shield the nitrogen. If you had a methyl group on the first position and a methyl group on the 8th position, 1,8 dimethyl carbazole, that would be completely protecting that nitrogen atom. So when we talk about particularly migration distances is probably the most well-studied aspect of the application of carbazoles to petroleum exploration. It has to do with the ways in which the methyl groups can protect this nitrogen, because if that nitrogen has no protection, it's not going to make it very far migration distances. So we'll look at the relationship of shielded to unshielded carbazoles to, in a qualitative sense, tell us how far this suite of hydrocarbons has traveled.
And does it matter if that migration is occurring within a sedimentary section as opposed to occurring within a fault zone?
There have been studies which show that it doesn't apply in the same way with migration through faults and fissures. I think that's a Clegg maybe 1998. And so, yeah, not the same relationship through faults. That would apply more towards sedimentary migration.
Okay, and her work was done primarily in a section in which she had enough knowledge to make that distinction between migration in the fault zone and migration within rocks.
So you think that would be like geographically specific?
Well, that's what I'm asking. In other words, was the learning set that she used to come up with that conclusion applicable globally, or was it something characteristic of the place she was working? It was in the Posidonia, if I remember right, in Europe.
I'm gonna have to go with my first I don't know on this one.
Okay, that's all right.
I don't remember the set of samples that she was using to make those determinations.
Okay, all right. I asked that question because it sort of has an applicability overall, because it's always going to be of interest how your dissertation work here, and this is not just the carbazole stuff, but the UEP work as well, how it's going to apply to something in other places besides Northern South America. Is there something characteristic about Northern South America that your results are going to be confined to, or is it applicable globally?
Right, that makes sense. I think the OA2 is definitely something that brought my attention to Northern South America, just because of that nearby Caribbean LIP, but it's an OAE, it's a global event. So that would have to be, I mean, it would have effects potentially all around the world. It just initially brought my attention to Northern South America for that reason, but I see your point.
Okay. All right. Very good. Thanks. That's all from me.
Cool. Thank you.
Nice presentation, Daniella. You've done a really nice piece of work so far, and it's been a pleasure to watch you move through this over the last couple of years.
Thank you.
I do have a couple questions. I'd like to start actually with following up to the questions you've just answered. And that was about age control. So this is not necessarily a question, but a comment to which you can reply if you want. You mentioned that you had two types of chronostratigraphic data. You have some biostratigraphy, and then you have sedimentation rates. But just be really cautious that if you're interpreting sedimentation rates as an additional data set, they might actually be from the same chronostratigraphy data sets. So a sedimentation rate calculated by somebody else may not be an independent set of chronostratigraphic information. It's just somebody else calculated rate using the very same chronostratigraphy you're getting. So it's like you're inputting the same thing twice, potentially.
I see. Okay. I did not, I guess my comment to that is I did not even think about that, and that's a very good point.
Okay. So yeah, just be careful of what's true data, independent data, and what is just, recycled, reused, repackaged information. Okay. Can you go to slide 18? believe that's the one. So I'm going to ask two questions, one sort of simple, just explain to us how things work question, and then one sort of broad philosophical approach question, both on this slide. So here on this slide, when you were presenting it, you mentioned upwelling, oceanic upwelling. So can you tell us a little bit about where is the upwelling and what drives it, and what's making the upwelling happen? Where is it concentrated and how much is it?
Sure. So I don't know if I'm going to answer the questions in that exact order, but I'll try to hit them all. So upwelling is something that happens either set on by effects of OAEs, OAE2 in particular, or it's something that is related to just seasonal changes in the water column. So it can be used as evidence for OAE2, or it cannot, depending on all these other external conditions. So where upwelling would occur would be in the deepest sections in the deep basin. So the blue that you're seeing in the scale, I know it's very small. So this shelf to slope is the light blue, deep basin is the dark blue. Mapping the slope edge is so important because we wouldn't get upwelling up on the shelf to slope environment. It's not deep enough for those upwelling processes to occur. So we want to know, the shelf was still connected at this point. When was the onset of, or when was upwelling based on the time of year and based on ongoing OAEs? When were those upwelling effects able to reach the division of Guyana to West Africa? But having said that, upwelling was considered to be previously just an absolute necessity to source rock deposition and preservation, and now there's kind of a rethinking of the parameters that are necessary for the creation of good source rock. So now it's considered more as it is great to have upwelling, but it's not the only parameter that matters, and there are ways to generate good source rocks without upwelling.
So looking at this image that you have on the left, can you sort of show us with your pointer where you think the upwelling would happen?
I think that the upwelling would happen, and I should say this is an educated guess. I think that the upwelling would happen coming up here, coming up the deep basin towards the shelf slope. It would also come from kind of the northwest down in this direction. Okay. And maybe again right here. So I'm imagining these upwelling trends as they reach the shelf slope.
Okay. So in a generic sense, not your study area, but just generic, how the Earth works, what makes upwelling?
Trying to think of a way that sounds educated to answer this. So I know that it has a lot to do with global currents and the shifts in global currents, and the movement of the productive biogenic activity towards the bottom for subsequent preservation, and it's this process that kind of cycles through the oxygen-rich sections to the oxygen-poor sections. And I know this answer doesn't sound good. I should have thought through how to explain this. But
okay. So you're right, it is complicated, and it is driven both by water densities and also by, as you said, global circulation. A lot of upwelling is a very sort of simple process driven by winds and the Coriolis effect on Earth. And it happens on really large scales, right? Coriolis along all of the west coast of all of the Americas can be or the upwelling is driven by these really large circulation cells and local, density differences, et cetera. But I wonder, in this very small area where you showed us on the, southern, the enclosed part of this area on your map, how upwelling works in this very sort of small enclosed basin. I wonder if you have enough space for all of that to develop easily. And I don't know the answer. Maybe you do, but I think it's something you should think about if upwelling can really happen there easily.
And I don't know if this is an idea too crazy as a follow-up to that, but when you were going through your explanation, the thing that popped into my mind was not whether upwelling could reach it to such a small area here, but whether this was shallow enough and the effects of upwelling were strong enough that the effects kind of could skip over this shelf environment, or if that would totally divide potential effects of upwelling.
I was actually surprised that you said, so the upwelling couldn't go across the shelf. You said that a little while ago. Why not? I have no problem with upwelling impacting the shelf at any point. You have to have the deep water also, but absolutely, it can reach the shoreline in the right scenarios.
Okay, yeah.
Could I jump in for a second?
Please.
Part of upwelling is related to surface wind, right? That's what
I said, yeah, winds and Coriolis.
Right, pushes water seaward, and that creates space for the deeper, colder water to come up and replace it. So, and who knows? Well, I guess maybe some people speculate on what the wind patterns were in this sort of early opening.
Yeah, there are wind reconstructions throughout the Mesozoic.
Okay. Anyway.
And again, it's just something to think about if it's how it's going to be affecting your rocks. You can't just say, oh, upwelling. It's like, oh, that's something I don't have to worry about. Oh, it just upwelled somewhere. We have to think about what's going to drive that where. Okay.
That makes sense. This is on my to-do list of, I had a to-do list of background readings to do before the meeting today, and should have made it to upwelling, but I did not, so I will this week.
It might affect your section differently in some areas than others. Okay, so my more philosophical question about hypothesis 2 here. And so hypothesis 2, you say that the modeled geographic transition in organic facies occurrence can increase resolution of paleogeographic maps. Do you really think that modeling increases the resolution of maps?
I guess a two-part answer. I do think that modeling increases the resolution of maps by increasing the accuracy of what the maps are showing and the boundaries that they're designating. So I will admit that it is not, in some areas, these small shifts or this increase in resolution, I say that because I want to base them on data rather than I'll draw a line through here, I do think that they in certain areas, they can have really very strong implications on how we're using these maps overall, what these maps tell us, particularly in Guyana. There are other areas where it is less important to understand, for example, the exact location at high resolution of the shelf edge, but those areas maybe that are, and I know less important isn't the right term, but those areas that are less important help us to connect areas that are very important. And so my answer is yes. I think that it is important and accurate and increases resolution.
As somebody that makes maps, I might disagree. And that's not to say that models are in any way unimportant or that you shouldn't do them or that we shouldn't use models to help understand the time slices or the gaps between maps. But paleogeographic maps in and of themselves should be based on data. They should be precise. They should be, based on a data set that is explicit. And if you're then going to bring in modeling to fill in time slices between those maps, or go down below the resolution of your data sets, I would say it's adding interpretation, it's adding a cartoon, it's adding a model, but it's not the same thing as the resolution of your map.
If I could sort of interject something there, and I agree entirely. Modeling exists because there are areas for which we have no data.
Right.
If you have solid data, every micron from here to there, you don't need to build a model for that area. And so I would just be, as you're going through your dissertation work, I would just always be concerned that there is a distinction between data that go into a model for the purpose of ground truthing a model. There's a distinction between that and the output of a model. And the output of a model is not data. The output of a model is an inferential conclusion. I mean, it's very useful. Don't get me wrong. Models are critical for the work that we do. But it's always important to make the distinction that data is real life, modeling is not.
Exactly.
Maybe if I could ask for a clarification on, so I'm using the model geographic transition in organophages, not as this map that I created that shows these blobs of organophages transitioning into one another, but at, like, let's say I have the well data for this well right here. And let's say at ACME 101, I have a sample that is well tied to ACME 101 or 101 million years ago, and then based on the quantitative geochemistry, it's indicating that this should actually be organophages B, which would mean that it would be deep basin rather than shelf to slope. That would be a way to kind of adjust this line a little bit, right? Because the organophages that I'm seeing in this one well are technically modeled, but extremely closely tied to the quantitative geochemistry.
Yeah, I think the distinction there is that you can sort of say there's two kinds of modeling. There's conceptual modeling and numerical modeling. The organophases stuff that Andy's published, that's a conceptual model. It's an idea of dividing organophases into an A through F structure based on the way these things look around the world. The distinction there, when you go to numerical modeling, and numerical modeling is things like global circulation models, or basin mod or petramod or something like that. When you're doing basin modeling, that is actually modeling that is ground truth by using data on the front end, real data on the front end, to see if the model successfully predicts those real data. And if the model does, then you have a little bit more confidence that the model is good in areas between where you have data. So, and you're actually going to be using both types, conceptual modeling and numerical modeling along the way. So it's an important distinction to keep in mind.
Daniella, I would say this is very much like my question about using SED rates as chronostratigraphic input. That's confusing a real data point with a estimate. And here we just have to keep these models, just, again, you don't have to do anything differently in any of the work, I would say. Just keep the description and the language clear in your head and in your rating so that we are always clear on what's input versus what's output, what's real data points in some form of a presentation versus what's an estimate or a model.
Okay. That makes sense, and it's on my notes in front of me in like all caps, really big words.
Okay. Yeah, but again, I agree with the other comments just here on. I think we're trying to say the same thing on how you should be approaching it.
Okay.
And that's all I had.
Oh my gosh, I even built a sequence stratigraphy slide. Okay, let it go. Are there any other questions from anybody?
Are we able to ask?
Yeah, if any of the visitors would like to ask, this is a good time for that.
Okay, thank you, Dr. Mann. So I have 3 questions. The first question is, what makes the well a good candidate for the UEB model? The second question is, are you able to use any kind of other types of correlation, like radiometric dating? Maybe if you have well logs, you can do well correlation using the well logs. Besides, you will have your biostratigraphic data, so you can have like a solid correlation and edge control for the sequences you have. And I think these 2 questions may answer the third one. So you can, if you answer this, that would be great. Thank you.
Okay. So for the first one, what makes well data a good candidate for UEP modeling? First and foremost, it has to have the minimum requirements of TOC, HI, Tmax is particularly helpful, and then it has to have, it can't just be, we drilled 3,000 feet and here's all the data and like no geologic divisions at all. What I'm looking for is like this minimum type of geologic division where they may even be lumping all of the Maastrichtian interval together and lumping all of the Santonian together. But at least I can break that up into million-year intervals later. The final thing is some indication of organofacies, and it's important to not rely on literature and to find like a kerogen type in a specific area, just because it varies so drastically through time. And it's a function of kinetic parameters, meaning that the use of an incorrect organofacies type will drastically change the generation that you're modeling. So that's what is required for well data to be a good candidate for UEP modeling. Additionally, what is helpful, so those are all the things that are minimally necessary to run a UEP model, but the things that make well data a good candidate for UEP modeling are these things, kind of like what you mentioned, like additional age indicators, or in some of the example, like I presented the UEP map across Trinidad, and I think it is, oh, here's a version. I have in my backup slides like these unobstructed versions of figures, but in Trinidad, for example, I wouldn't necessarily call the wells that I used right now good candidates because I got them just from the literature, where I was only given one value for geologic age and had to make the assumption that the incorrect assumption that geochemical parameters are consistent across their entire geologic age. So I would say what makes something a good candidate would be additional age indicators, additional good data-driven age indicators, and second, a high resolution of sampling. So Guyana over here, especially well 1, it looks absolutely fantastic because they took samples all over the place, just continuously. So there's so much data that, and this is actually the well with the highest UEP. UEP is just modeled, it's shown cumulatively, and these intervals are so skinny. But this is really the resolution that we're looking for that is dependent on a very high volume of samples. And then second question, you brought up radiometric dating. I think that is a good quantitative age indicator. I just haven't encountered that in a lot of the well data that I have looked at so far. So yes, I'd love to use it. No, I have not had the chance to do that yet. And did it answer your third question?
I think the last question will be like, yeah, the answer is very great, and I'm sure that you will do excellent job with your PhD. So how the model will be dealing with unconformities?
So with the unconformities, those really come into play. Oh, too many slides. These come into play when we're trying to understand the lateral continuity of units. And the first thing that I've learned is that nobody in the literature seems to agree on where these unconformities are, the extent, the like amount of eroded section surrounding the unconformity. So what I did for now, and this is kind of what I mean by the individual erosional sections, will refine the unconformities that we see here. What I've done is previous in literature, for example, the mid-Campanian unconformity was reported as cutting out a big chunk all the way over in Trinidad even, but definitely in nearshore Guyana. And then when I looked at the nearshore Guyana well and saw that there wasn't any kind of break, there was no skip in TOC, there was no skip in these indicators of the thermal history. It didn't seem likely. I mean, maybe if there is an unconformity, there just isn't erosion related to that unconformity. It would more be potentially a hiatus, but we're starting to correct, and that's what I mean by refine this chronostratigraphic column based on well data. Another reason, though, that unconformities are really important, and it's kind of an excuse to skip to my sequence strat slide, is just looking preliminarily at sections in Guyana and trying to divide them up into high stands, low stands, and transgressive system tracks. What that has kind of shown us is that the acmes that have been identified as significant so far show up largely in the TSTs, sometimes in the HSTs, and not really in the LSTs. So this is another reason why these unconformities are so important, is because they, at least this is the one of the ways that I use to separate out these individual system tracks of sequence stratigraphy. And this is very bad, very preliminary example, I know, but that's another way that they're refined in the chronostratigraphic column, used to differentiate system tracks, and are a big part of this project. So,
thank you so much, Daniel.
Yeah.
I got a quick question, or sorry, I got a quick question about the La Luna formation. You made the statement that you don't think the La Luna is a good term, and that it's sort of overused and may not be relevant as far as a source rock in the Guyana area. Yet on your chart, you show La Luna is Santonian, right? And that overlaps with your Guyana source rock age. So putting the name aside, I mean, doesn't it have a lateral equivalent in Guyana, which they call the Canje Formation? It just seems like you were ruling that out as a correlative lateral facies, yet it's got the same, or it's in the same age range.
I'm going to answer your question with kind of another hypothetical, I guess. Because I was in a conversation with Brian Ott recently about, well, what makes two rocks equivalent? Is it actual age equivalency? Is it equivalency of their lithology, equivalency of their organic parameters? So I definitely, the Luna Formation doesn't extend all the way into Trinidad and Guyana. There is potential that is correlative with those areas, like you said, the coniation section here. But as far as calling them fully equivalent source rocks, I still wouldn't do that, only because limestone, carbonate, La Luna Formation, shale, clay-rich Canje Formation in Guyana, they have totally different kinetics, totally different oil versus gas outputs, totally, the petroleum systems that they are starting in those two respective areas are very, very different. So I still wouldn't call them equivalent rocks. I would only refer to them as age equivalent. But again, that's only a statement that I can with confidence say when the UEP modeling has been completed throughout the La Luna formation, and I haven't done that portion of my project yet.
Okay, got it. All right, thanks. And whoever was speaking, go ahead.
Okay,
Yeah,
so I'm glad that you could make it.
yeah, I'm Fausto Mosca from Total Energy, and I have a couple of comments that I would like to make. One that would be a paper presented at the AAPG from joining Apache and Total, and there will be some clarification on the source rock. So I guess you will attend the meeting, and you will see where we are now with our knowledge. But my consideration,
For the upcoming image conference.
yeah, the one is coming this year.
Okay.
Here in Houston. The comments are that be careful when you use well data, especially coming from the industry for your calculation of the UAP, because simple consideration, the industry, unless we do a bad job, we try to locate the well where there are the best conditions for reservoir deposition. So therefore, the source rock is always underestimated at the well, and you can be biased. If you look at the data of source rock from wells, sometimes you wonder, how do we have, where billions of hydrocarbon are coming if my TOC is barely above 1%? Second point, most of the time we have cuttings, huge underestimation, huge dilution, especially if you have different lithology than shale nearby. Sampling frequency is very important. If it's 50 centimeter and if it's 5 meter, it makes all the difference. If you have a sidewall core, you can do a better job. If you have a core, you can do a great job. Unfortunately, we have core only in unconventional and not in conventional in core, but in source rock, but it's okay. This is just one consideration. So to me, in my experience, practical, when I look at the TOC data coming from cuttings, I always multiply by 2 or 3 to have what I believe should be the best condition in terms of source rock properties. In the depot center, in the best condition for the preservation of the organic matter. The other consideration is that if you want to do comparison between different source rock in different basin, probably you are aware, but there is an old paper from the Maison Huizinga where they describe the SPI index, and I posted in the chat the paper. That is a nice way because it's also take into account the type of basin drainage that you can have, vertical versus lateral. As you know, Guyana is mainly lateral, so unless you have deep focus, that's one of the problems to send hydrocarbon up to the very shallow reservoir, let's say Maastrichtian, because you need some deep focus to send them vertically. Due to the fact that it's pretty flat, you have a mainly lateral component in charging. So that's a way to try to compare different basin. And last but not least, we notice, I cannot go into detail, but there is an extremely variability in space and in time for your source rock. So whatever is the source rock here can be a totally different source rock here because there is this strong variation. And I put the definition of all the different euxinic global event because, yeah, we are used to since I'm Italian originally, 2 famous Italian geologists, Selli and Bonarelli, but there are several other. You see, even in the Albion, there is a lower Albion and upper Albion. So depending on the resolution of your biostratigraphy is really important because the lower Albion has a different property than the upper Albion. And there can be a lower cognition, et cetera, et cetera. So your before I think Joe pointed out to the importance of the date and the age, and I truly agree that that is a key point. All right. But a great presentation anyway, great program. Thank you.
Thank you. I have a quick follow-up question on the first point you brought up. I'm going to pull up a slide in the meantime, but so I wanted to show you that the point you made about the Albion, just in the preliminary work, and I know it's not totally defendable at this point, but we do see this gap in UEP that occurs right in the middle Albion. So what's been pretty cool so far is we can see this separation of the upper Albion and the lower Albion, just like you had mentioned. And I guess my question back to you was about the first part you said, where I understood the concerns that can come from the well data and industry, like you mentioned, and how one of the workarounds is working with core. That would be obviously better to take a look at the source rock. But I'm curious about if I can't get access to core and I'm kind of stuck looking at this industry well data, is the solution to just keep a closer eye on, don't always like believe what I see in terms of age, or are there any suggestions that you would have to the concerns in your first point?
Well, let's say that if you have, and I've seen you have data coming from the ODP, or, well, those where you have those condensed section, that's telling you that you see there, if you compare that with the well there, you have TLC can be 10, 15%. You look at the well and you come up with 1.5, 2%. So clearly to me is more than 1.5, maybe that 15%, the 20% that you can see at the ODP side, it can be clearly because you have this string condensation. So then you have a opposite problem there with the thickness. That is not maybe an effective source rock in terms of thickness. So to me, that is giving you some idea how in the best possible condition what kind of properties you have. I know that you don't have the type of data that I have access to clearly, but you can do a kind of inverted geochemical calculation. If you know the oil originally in place in the basin, more or less, you can come up with what kind of properties my source rock should have to generate, expel, including losses, that amount. Because you have billions of hydrocarbon inside Guyana and Suriname. If you consider all the losses, you will come up with some super astronomical source rock. Otherwise, you cannot justify the volume in place.
So yeah, that makes complete sense. We have started on like a back calculation of the original TOC and original HI parameters for that reason, to try to, and we are we're subtracting the volume that already has been produced through part of that calculation as well, essentially reducing the S1 modeled pyrolytic value. So I think that we're off to a good start, but I'm definitely going to take your suggestions and build those in as well.
All right, very good, excellent.
Good to see you again.
Okay. Yeah, thank you, Fausto. So I think, are there any other questions from anyone? Because I think we're about at the end of our public presentation. And what we normally do at this time is we're going to ask the people that are logged in who aren't members of the committee if they could log out. But before we do that, I see Trisha Alvarez is here. Trisha, do you want to just introduce yourself to the group?